Welcome to this week's Center Welcome. I'm Giamarchi from Rice University, and it's a great pleasure for me to introduce Professor Thierry Giamarchi as a speaker today. So Thierry got his PhD from University of Paris, spent a couple of years visiting AT&T Bell Labs in the 1990s, was in the CNRS system, and since 2002, he's been a professor of physics at the University of Geneva. So I've known Thierry for a long time. Thierry is a superb physicist. His research has covered many areas within theoretical condensed matter physics, and this includes four-dimensional systems, quantum mechanism, and disordered systems. Thierry has been recognized by many honors and recognitions, including membership in the French Academy of Sciences. I might also add that Thierry is known to play magic card games. Now, I wasn't sure whether I should mention that in this forum, so I checked with the higher authority. ChatGPT said that he enjoys the game because it combines skills that are fully aligned with his expertise in physics. I think that gave me the license to mention this. So today, he's going to tell us about the magic of quantum transport. Without further ado, let's welcome Thierry.
Okay, so first, thanks to all for being here at this colloquium. It's a great pleasure for me to have Chimiao as an host. As he said, we know each other for a long time now, about 35 years. So it's a great pleasure to have him here. I want also to thank the organizers, both of the program, which is called Probing Collective Excitations via Quantum Transport and Spectroscopy. So you can, yes, there will be connections, but also of the working group, which is headed by Jörg Schmitzmeier, who is here, who covers more cold atoms, and you will see that there will be also some cold atoms in this talk. So you know from Chimiao what is the program. I'm going to cheat you during 1 hour. That's the idea of the colloquium. No, more seriously, I've been told to do this colloquium mostly targeting the other program, so the biology program. So this is what I will try to do. So don't hesitate if you have any questions. And by the way, for the biology program, if you have any question on quantum transport, address them to Ned Wingren. Ask him why I'm telling this. Okay. Because of the sort of broad nature of the colloquium, I'm not going to show the usual list of collaborators. But I cannot, of course, resist showing you a picture of the group in Geneva. I will, of course, talk today largely about other things than what we did in the group. But if you want to know more on what we do, I refer you to the website and don't hesitate to go and see what excites all these young people, a lot of them working on quantum transport one way or the other. So I'm supposed to tell you a nice story, and it's very difficult to find the proper level of equilibration. I feel a little bit like the people in this movie, whom I'm sure you know. If you don't know it, I highly recommend it. It's trying to find a proper language to talk to aliens or to learn alien language, arrival. So don't hesitate, interrupt, ask questions. Don't wait till the end of the colloquium if there is anything. Yes?
The microphone a little bit away from here.
Yes. Is it better? Okay. I hope it's also good for your eardrums and nobody is bleeding through the ear. I tend to speak relatively loudly. Okay, so we are going to talk about transport. And the idea behind the title, it's both a joke, of course, is there a difference between an electron and an autobus, which is try to say, is there a difference between classical and quantum transport? It's not a complete joke. I remember when I was at Bell Labs, I heard a seminar by someone named Rolf Landauer, was an extremely prominent physicist in quantum transport, where he told that he was going to give talks everywhere. And one time he went to a conference and he gave a talk on transport. And at the end, someone asked him, I'm not sure I understand, how many people can you put in an electron? He realized he had been invited in a conference on urban transport, and it was not exactly his field. So I still remember this, so that's inspired the title of this colloquium. So let me just say that certainly in condensed matter, transport is really a routine probe for new materials. Every time you synthesize something new, the first thing you do is to measure its resistivity. And that's kind of the most naive thing you can do. You put a battery, you pass a current, you have your mysterious system, which is here. And in a way, this gives you information on whatever are the properties of the material you're trying to look at. The typical situation by which people do transport is the one which is above here, where there are two reservoirs of particles with an imbalance in population in these reservoirs. Here, the two reservoirs are in the same battery. And then usually you have a little piece of material here, which is the lamp on this drawing, that you're trying to probe with this technique. I just want to emphasize that this is not the only situation that you can study and in which you can do something resembling transport. I just show another situation here, which is called STM, scanning tunneling microscope, where in a way, what you're trying to do is to pass a current between a probe, which is a boring piece of metal here, and your other electrode is essentially the material you're trying to study. So this is something which is a little bit different, but this is essentially the same phenomenon. I won't say much on this situation during this talk. I will concentrate mostly on what I would call the canonical transport with a battery and a system in. Now, very often when we study transport, what we do is we cheat because we consider that the voltage here, the object that is creating the imbalance in the current, is relatively small, and we use linear response. We assume that the current is small, the voltage is small, and therefore we probe the material very close to its equilibrium properties. I want to emphasize strongly that studying the transport is a non-equilibrium phenomenon. And technically, every time we are out of equilibrium, we lose all the tools that we have from statistical physics. We don't even know if defining a temperature or something like this is valuable. But, you know, if you're not very far from equilibrium, you can say, I can study this object here, which is the ratio between voltage and current, which people call the conductance, by using equilibrium properties of the material. And of course, you can do this for quantum matter, but you can do this for classical matter. This is something that we know and love in many situations. I also want to emphasize, and I will not insist too much on this during the colloquium, that in effect, when you have a new material, when you have something, when you want to use a material, usually the property that interests you most is what is its transport property. After all, we like copper because it does good cables for our electrical appliances. And if we had to do the same thing with silver, it will be a little bit different society in which we would live because the cost of transporting energy would not be the same. If you have materials with more exotic properties, you usually are very interested. I'll show a couple of examples on is it a good conductor or is it not a good conductor? Okay. So now let's go back to electrons versus autobus, namely quantum versus classical. And if you think about classical particles, we can write transport equation for classical particles very well. It's known as the Fick law or diffusion law, and this is something which has been worked out in various contexts by various people, not among the most ignorant among the physicists. And in particular, we know that, for example, if we have a little bit of disorder will lead to diffusion of the particles, namely the motion of the particle will give to a mean square displacement which is proportional to the time. And this leads to a mobility of particles that we can study, which is connected to temperature by this equation. Now, of course, when you go to the quantum world, you would say, haha, particles are waves. And what does it change? And the answer is nothing. When you do the calculation of the conductivity of a metal, you find the extremely boring result that you could derive in two lines by viewing the electrons in the metal as little spheres bumping into each other, randomizing the momentum, and you can, it's a boring formula. Its conductivity is proportional to the number of particles, okay, the charge divided by the mass and the lifetime, mean time between collisions and so on. So it sounds like there is no difference between an electron and an autobus. And of course, it would be very boring if this was the whole answer. And there would be no Aspen Center of Physics program on collective excitation probed by transport, for example, if this was the end of the story. Actually, you would even say something worse. You would say, oh, for a quantum problem, the disorder or scattering plays even less role than for a classical problem. Because for a classical particle, if the diffusion potential is larger than its energy, it doesn't go through. It cannot go through the mountain here. But for a quantum particle, it can tunnel through the potential. So you would say even for a quantum problem, the scattering is even less important than for a classical problem. So this is the naive answer. Of course, this naive answer is completely wrong. And I will try to show you in an increasingly complex way how this picture is wrong and why it's very important that there is quantum in the world, quantum transport. The first thing that people noticed is that the wave nature, and this now I'm talking about things which are 1 century old. We'll go down to today a little bit later during the colloquium. What people noticed is, of course, when I told you, oh, it doesn't change anything, well, one has to be a little bit more careful. Why? Because solids are periodic objects. Here is the beautiful hexagonal lattice structure of a compound like graphene, for example. And you know that if you have waves propagating in a periodic potential, there is, if you solve the Schrödinger equation, there is a theorem, which is called Bloch theorem, which tells you immediately that only certain waves are authorized to move in this periodic structure. And not all the waves, not all the wavelengths are authorized, which means that when you look at, how can put particles in a solid, well, if it was classical particles, you can put as many as you want. It doesn't matter. But if it's quantum particles, and as you start filling the possible states in a solid, we'll notice that only a certain range of energy are authorized inside a solid. This is the concept of energy bands, and this is also resting on another principle of quantum mechanics, which is totally amazing, and that has absolutely no classical equivalent, which is called the Pauli exclusion principle, which says that two quantum particles, if they are fermions, cannot be in the same quantum state. If you think about it, it's completely nuts. It's particles which have no interaction between them. They don't see each other. They know perfectly well what is the quantum number of the neighbor. They know they should not have the same quantum numbers. Just like if you arrive in the morning knowing that you shouldn't have the same shirt color than your neighbor. They don't know how particles, how fermions achieve that in a solid. They achieve that in the whole universe, as you know.
Autobus obey some papers.
Yes, all particles obey this principle in the universe, and the universe is separated in two. There are particles which are called bosons. Their wave function must be totally symmetric. By the way, we are celebrating this year the 100th anniversary of the discovery of this by Bose in particular. And there are other particles which are called fermions, and their wave function must be totally antisymmetric, which means that you cannot put two electrons in the same quantum state, which means you feel here the energy state one by one. And then once you have filled this state, that's finished. You cannot put one more electron without putting more energy in the system and starting again to fill. It's like a sugar box, you know, where you put little sugars, except here it's the repulsion that prevents you from putting many sugars in the box. Here, it's not the repulsion. It's the Pauli principle. Okay, electrons repel because of Coulomb and blah, blah. Let's forget that. Doesn't matter. Okay. So in a solid, we have these energy bands, which means that now people understood that if you feel exactly one of these bands, it will be extremely complicated to excite something here to the next possible state. So a state where you have filled the sugar box is an insulator. There is no way you're going to transport anything here. Nothing can move. Everything is blocked. To unblock something, you need to go to the next end, and so on and so forth. On the other end, if this is half filled, for example, you would get a good metal because you have plenty of excitations which are possible. And if you're nearly filled or nearly empty, you have what is known as a semiconductor. So this quantum principle, this very simple quantum principle, gave you the understanding of what materials are insulator, what materials are metals, what materials are semiconductors. And you could say it has no importance because we know that quantum mechanics only apply at very, very low temperature and in laboratories, not in real life. This is completely wrong. A solid has a characteristic energy scale, which is 1 electron volt, which is 12,000 Kelvin, which means this piece of metal is quantum. And I can touch quantum mechanics. So if I want to understand the properties of solids at ambient temperature, I have to take into account quantum mechanics. I cannot ignore it. So this is fantastic. Quantum mechanics predicted most of the property of simple solids, specific heat, the transport, and so on. And it means essentially it gave us the mastering of material. And I won't have to insist how materials are important for our society. There are all ages of the society that have been labeled after one material. You have the age of copper, you have the age of bronze, you have the age of whatever. I'll let you decide what the 20th century should be labeled. I will give you an answer in 1 second. This led to a complete change of our society. I think most of you are too young to even know what this drawing means. Okay, for people like me, this is a vacuum tube. Okay, or if you're very rich, now there are Wi-Fi amplifier that are sold at an incredible price. So this is a way to amplify. You know, you have an electrode emitting electrons. You have a voltage here which can deflect the particles, and you have another place where you capture them. And depending on the voltage here, you control the flow of particles. And of course, this is a fantastic way to control, to make amplification. And in 1947, for example, one of the first computer, the ENIAC, was built with these tubes. And here is what journal, serious journal, was saying on the ENIAC. It said, where a calculator on the ENIAC is equipped with 18,000 vacuum tubes and weight 30 tons, computer in the future may have only 1,000 tube and weight only 1.5 tons. Okay. So why is it wrong? Well, it's wrong because we live in the Silicon Age. We live in an age where people understood what is a metal, what is an insulator, and what is a semiconductor. And these three gentlemen Hardin, Bratton, and Shockley managed to invent the transistor. By the way, just to make a little bit of advertisement, Bardeen is the only physicist who got 2 Nobel Prizes in physics, one for the transistor, and we'll see later for the other Nobel Prize. So, of course, this has changed completely our society, and this is a direct consequence on the fact that there is quantum transport and not classical transport. So this is something where we live in the information society that we are in because of the fact that in a stupid solid, we have quantum physics. Now, all this that I told you is one particle physics. I look at the electrons one by one in a way. I don't care. They don't interact, which is, of course, completely wrong. So can we get away with this one body picture? And we understand very well free electrons. As I said, we can solve the Schrödinger equation. But in real systems, I can take aluminum or whatever, we can also estimate the repulsion between the particles. If you do this, you will find that this energy is also 1 electron volt, is also 10,000 Kelvin. So the message is you cannot neglect the interactions between the particles. So you could say maybe all what I described to you, I will not say the word, but you understand what I mean, because at the end it will be like little classical particles which repel each other, and I should more worry about the repulsion between the particles than I should worry about all these quantum effects. And the question is, what are the properties of real systems? And this is a very challenging question. And the person who saved the day is Lev Landau, which I am sure needs no introduction to this crowd, and who built in the, let's say, 1950s, in the broad sense, a theory which is called the Fermi liquid theory. What Landau showed, which is another consequence of quantum physics, is that actually free electron theory is largely applicable. And there is a price you have to pay. The excitations in a solid are not free particles, but they are dressed particles. A little bit like you could say an electron is surrounded by a cloud of photons, and this is the new particle you should consider. An electron should be surrounded by a drop in density in the other electrons. But if you take this into account, the only thing you have to do in first approximation is to change the mass of the object. And once you have done this, you can think of this as free excitation. The main idea is that you shouldn't think about the object as individual objects, but you should think in terms of excitation. What are the basic excitations? And what Landau told us is that in a solid, the basic excitations, they look like free electrons. They're not free electrons, are something we call Landau quasi-particles, but they will behave like free electrons. They have a different mass, not the bare mass, but they have the same charge than free electrons, and therefore everything I told you about one particle physics works. So our transistor works, and we can build a real computer out of it. Now, this was the 20th century. Now we're in the 21st century, and what has changed? First, everything that was valid before is still valid today. But the point is, of course, people have turned now also the materials, the situation where this Fermi liquid theory is not applicable. And we know many materials, we have many situations where we cannot sweep the interactions under the rug. And we have to worry about them. And they lead to novel phases of matter. I'll show simple ones and go to more complicated ones in a moment. But this is the main message. That if now we look at real materials, we have 10 to the 23 particles which have to obey the Pauli exclusion principle. We have to obey quantum mechanics. We have to have a wave function which is totally antisymmetric, but in addition, also interact with each other. And what are the consequences of this interaction is highly non-trivial. It's not just complicating the problem, it's changing the nature of the problem completely. So you have to face a novel situation situation where we have novel excitations, something different from the Landau quasi-particles. And these new excitations, they can be probed by transport. They can be probed by other probes. Transport is, of course, our working horse to try to understand what is the nature of the excitations that exist in a solid. So we are working extremely hard to study the transport in these new materials, in these systems, for which we cannot hide behind Landau's Fermi liquid theory. And this is an exceedingly difficult, because we have complexity of many degree of freedom, 10 to the 23. We have the complexity of dealing with particles which are waves, and the mysterious symmetrization or anti-symmetrization postulate of quantum mechanics. And we have to deal with the interactions between particles. So I'll show two simple examples, one which I'm sure you already heard of, which is superconductivity. Superconductivity is the fact that if you take a certain material, for example, here mercury, the original discovery done by Kamerlingh-Onnes and Holst, well, guess what? Transport property showed something weird. Transport property showed that the resistivity of mercury, when you were lowering the temperature, was getting finite, as any normal material should. And then suddenly, at a very specific temperature, was dropping to zero, or at least at the time a non-measurable quantity. It was staying zero everywhere below this magic temperature. So this is a magic transport property where you have a material which can transport without any dissipation. There is dirt, there is everything you want in this material. So by all classical version, there should be a finite mobility, a finite resistivity, but quantum mechanics makes it that this material can transport without any dissipation. All right. Of course, this is particularly interesting for applications, not with mercury, but with other materials. So why is it so? Well, it took a little while to understand why it's so. The explanation came in 1956. It was given by Bardeen. Remember Bardeen? Same guy. Bardeen, Cooper, and Schrieffer, second Nobel Prize for Bardeen. And it was complicated because it required quantum mechanics needed to be invented to solve for superconductivity. And it required new technologies for the time, which allow to take into account interactions between the particles, something called second quantization, for example. So, and it required good ideas because, Landau, Feynman, and all these very famous guys tried and failed. So this is not just because someone had the right computational technique, but also these three people had the right combination of talent to crack this problem. Okay, so this is one very simple example where you see that transport in a quantum object can be drastically different than anything we know in the classical world. In that case, we get a transport without any dissipation. We get a perfect conductor in a system which normally would contain dirt. So let me give you the opposite example, which is called the Mott insulator. So imagine I have a good metal. I told you if I have a system in which I feel half of the states in my band, I should get a good metal. Yes, that's true if you have no interactions. And this gentleman, Sir Neville Mott, understood that, well, it's true if you have no interactions. So let me show you a little cartoon. Imagine that you have a solid with particles which are able to jump from one side to the next. And I've put red and blue particles. Let's say this is spin up and spin down, for example. And imagine that now the particles with spin up and spin down repel. They have a repulsion, and when they are on the same site, it costs an energy U. Now, if it's the case, immediately you understand that hopping from one side to the next will be extremely disfavored. Quantum mechanics would like to have you go delocalized to be in a plane wave state here, but the repulsion would much prefer, like in an egg box, that you put one egg in every minimum of this potential. And if you do this, what you get is an insulator. Again, nothing can move. But this is an insulator that would disappear if you could switch off the interaction. And therefore, it's not a band insulator, but it's something which has been named after its inventor, Neville Mott. This is what we call a Mott insulator. So this time, oppositely to superconductivity, interactions are producing an insulating state where you would naively expect metallic state. In a way, the Mott insulator is a very classical object because you would get the same thing with billiard balls. If you take an egg box and you put one egg per minimum, it's a Mott insulator. So interaction there push the system towards something which is much more familiar to classical physics. Let me go back to quantum transport. This leads to very difficult questions. As I said, it's an out of equilibrium situation, and we lack drastically method to compute. We are still relying on methods which have been invented in the 1950s. One is called the Kubo formula. This is linear response. This is saying that the conductivity is the current correlation function. So we are studying fluctuations of the current. It would work also for classical materials, by the way. And another way of viewing at transport, which is adapted to the two reservoirs and structure in between, which is called a more mesoscopic version of transport, is something called the Landauer-Büttiker formula, which is viewing the transport as a transmission of waves from one reservoir to the next. And I won't go in detail on the Landauer-Büttiker formula, but this is a very beautiful vision of transport, which is complementary to the Kubo formula, and which works very well when you have non-interacting particles. And there is a generalization of the Landauer-Büttiker formula, which was done by Galmir and Ned Wingren, which is known as the Meyer-Wingren formula, which works also for interacting particles, which is why I suggest to redirect all the questions on quantum transport to Ned Wingren from the bio half of the. But these are techniques which have their own limitations. And of course, we are trying to find new techniques. And it's difficult. As I said, we have 10 to the 23 particles, so we won't write 10 to the 23 equations. Of course, numerics is an alternative. But again, the quantum nature of the problem makes it very difficult to solve on a classical computer, especially for fermions. There is something called the sign problem in simulating fermions on a classical computer. That makes it not so easy, and people are trying to find a way to crack this, or at least find an approximate way of cracking this. So we need to invent new methods, whether analytical or numerical. There is something called the density matrix renormalization group, which Uli Scholvok, who is here, is one of the leading scientists. So we are trying, but not easy. So a way to get away is to get help from another field and to use something called quantum simulators. Now, what is a quantum simulator? Well, this is something that was proposed, if I can say, by Inman, which is that you have to find a computer that is quantum in itself to try to solve a quantum problem. Now, how can you do this? There are two routes. One, which I will not discuss in great detail, which is digital quantum computing. Then the same way we have here digital computer, we could realize a computer with something called qubits, quantum bits. And this is an idea that has been proposed by several people, for which got, for example, the Fundamental Physics Breakthrough Prize. This is beautiful. People are working very severely on it. It's versatile, like any digital computer. You can program it and solve, in principle, any problem on the planet. But for the moment, it's a little bit difficult. So there is an alternative which exists and works. And for example, Jörg is a main player in the second category, I would say, the yellow category here, which is quantum simulation. What does it mean to do a quantum simulator? Well, this is an analog computer. So what do? You find an experimental system that implements as closely as possible the problem you want to solve. And then you just read the answer on the experiment. On one way, you could say, I just do an experiment. But the experiment is not a caricature, but a precise copy of the model you're trying to solve. Let me show you an analog simulator, not a quantum, but for the division. If I want to simulate a division, I take a battery, I know the voltage. I take a lamp, I know the resistance. I measure the current. Current is the voltage divided by the resistance. The experiment gives me directly the division of V by R. Okay, now you want to solve a more complex quantum problem, and you have to do the same thing with cold atoms. And I will show you that this is a program that can be studied. And this has the advantage that either it gives you the answer, it guides your intuition, or it can help benchmarking some of the theoretical approximations that you will do to solve. Let me choose a couple of examples, and I have, of course, many more examples of quantum transport. We could last 1 week with example of quantum transport, but I'll try to take maybe 3 very brief examples. The first one is a very simple one. It's an impurity in a quantum bath. How does an impurity propagate? Imagine that I represent it in 1 dimension, but it can be any dimension. I have a gas here made of particles, which I denote as blue, and these particles are quantum particles, for example, bosons, and they are moving, they are interacting, they are as nasty as you want, but at some point you change one of the particle into a red particle. So it's like creating a red particle at time 0 at point 0. Then we want to know at a later time, where is your particle? So if the particle was alone, it's a simple problem of Brownian motion. Your particle would move somewhere in the problem. But here, your particle is interacting with the rest of the bath. The question is, how are the collision with the rest of the bath modifying the propagation of your red particle? Surprise is that you would expect naively, oh, it will diffuse. R square will be proportional to the time. That's what would happen for a classical particle. What you find is a very surprising result, which is imaged here, where you see the position of the particle as a function of the time. And of course, it's a quantum object, so it's a probability here that you see. And the big surprise is that the probability of finding the particle at point x and at time t is exponential of minus x squared divided by the log of t. So x squared is only growing as the log of the time, with subdiffusing. And again, this has no classical equivalent. Quantum gas around the impurity maintains the particle at reasonably close to the origin. I don't want to go in more details, just to show you that this can be realized. Yep, sorry.
Is that the result of a funnel, or is that trying to?
So this is an analytical result on the model that I showed above of particle interacting with delta function interactions and a different strength of interaction between the blue particles and the red particle. But one can also do numerical simulation. This was done only in 1 dimension, and this depends on this result is only in 1 dimension. The results, yes, depends on the dimension. Absolutely. Yes. 1 dimension is very special. I can tell you more why. There is something called the Anderson orthogonality catastrophe, which is not killed by the recoil of the particle in 1 dimension, and which is responsible for this behavior. In 2D, it would be a much more ballistic motion of the particle. Okay. Here is the experiment. This is a quantum horse race done in the group of Immanuel Bloch, and Stefan Kohr at the time. And each line here is one system like I showed before. And you don't see the bath, you only see the particles in red. And this is as a function of the time. They were all put at time 0 in this vertical line. And then for each horizontal line, the particle have moved a little bit further, and so on. So each line is an independent experiment, and you can monitor propagation of the particle as a function of the time. And you see the histogram, which tells you, by the way, that there is indeed interferences, and this is not a simple classical model. Let me move to a second example, and I think it's probably the only thing I will do in view of the time. Maybe I'll have time to mention the last example. Let me show you the example of one-dimensional system. Why is it interesting? Because in 1D, the excitations are very weird. And let me try to illustrate this. Imagine I have a quantum system with particles carrying charge and spin, for example, electrons. A priori, if I remove one of these particles, I will remove both the charge and the spin. And naively, this is what should be an elementary excitation. And it should propagate as such, but not in 1D. In 1D, if I let such quantum system evolve, trust me on this, I will flip the spins, and this is what will happen. Of course, this is a cartoon, but one can do serious calculations. And you will see that after a while, in a portion of the system, there will be two spins down close to each other. There will be no charge missing. So this object here looks like an excitation that carries spin but no charge. On the other end, I let the charge move here, and you will see that in another portion of the system, you will get a charge missing, but the spin environment is up, down, up, down, up, down, so it looks like no spin is missing. This is something remarkable that in 1D, the excitation can fractionalize into something that should not be able to exist because it's below the elementary excitation, which consists in removing one particle with a charge and a spin. And the reason it can, it's because it's a collective excitation. And of course, it would not live outside this chain. So we have the elementary excitations are something which people call spin-ons, which carry spin and no charge, and holons, which carry charge and no spin. And these are the elementary excitation that exists in our 1D interacting system. Now, of course, the transport will be a priori sensitive to the existence of these holons. So as it has consequences, well, yes, and you can test it on real systems. I don't want to go into the details of the systems. If you measure the frequency-dependent conductivity in this system, you will see that there is a characteristics coming from these holons, which is that this should behave as a power law, and this power law has been observed in these materials. And this is a confirmation of a set of properties which are the equivalent of Landau Fermi liquid theory for 1D, which were proposed by Duncan Haldane, who got the Nobel Prize for other reasons, but he could have gotten it for this kind of things, which is something called the Tomonaga-Luttinger liquid. So this transport measurement tells you that you have indeed these holons that exist. Now, can you test more precisely for the spin-charge separation? Again, I don't want to go in details, but the answer is yes, you can try. And this was done by Amir Yacobi in particular, who was there last week and gave a talk last week. And the way he did it was to engineer tunneling experiment between two quantum wires, two 1D systems, the idea that the spin-on and the holon should get together to be able to tunnel the next tube, to the next wire, and that should have consequences. This has consequences on the spectrum of tunneling, where you should see two modes, which is a little bit difficult to see here, but it should have also consequences in the creation of a moire spectrum, and the theory for that was done by Jaroslav Czerkovniak and Bert Alperin, and this is in good agreement with the observation. If you want to have a clearer evidence, go to a quantum simulator which was done again in the group of Immanuel Bloch, Munich. And in this system, they could prepare a gas of particles with spin and charge, and then image directly the spin and the charge of the material. So clarity here, the box have been split. So when there is something in the upper box, it means you have a spin up. When you have something in the lower box, you have a spin down. When you have nothing, you get a hole. And here you have a spin up, here you have a spin down, and so on. And you see exactly patterns that resembles the little cartoon that I showed you. And this is our quantitative measurements that can be done on this. And by doing this measurement, you can check indeed that this spin charge separation is actually existing. There are different, but experiment also measuring the spin charge separation in the group of Randy Hewlett in Rice University, which are absolutely beautiful, but I won't have time to talk about them. Now, can you see other consequences if I go back to condensed matter of this spin charge separation? Yes, because I told you when the particle need to go from one chain to the next, they need to recombine, and you need to put together the spin-on and the hole-on, and that's not easy. So let me show you one consequence, and that's the only thing I will say. Look at this transport. This is the transport along the chains as a function of temperature. You see a very good metallic behavior because the hole-ons are moving very happily along the chain. If you measure the transport perpendicular to the chain, you see that the resistivity is actually going up and the temperature is going down, which tells you that your material is a good metal in this direction, but is an insulator in the perpendicular direction, which is crazy. It's not crazy. The hole-on propagate very well along the chain, but if you want an electron to hop from one chain to the next, you need to put back together the hole-on and the spin-on, and that's very difficult, and this will happen not very well. So as long as the system stays 1D, the resistivity is going up, but you see that the transport is also telling you that something magic is happening at this temperature. And the magic that happened at this temperature is that the chains stop to be weakly coupled, the material become 2D and then 3D. So the quantum transport is a direct probe of the nature of the excitations inside the system. In this part of the temperature, it tells you the system is 1D, made of very weakly coupled 1D chain. In this part of the phase diagram, it tells you the system has changed dimensionality and is now more 2D or 3D system. In view of the time, let me skip this and maybe mention just the beginning of the last example, because I cannot pass this. I told you, quantum systems, when you put disorder, it's even worse than a classical system because it can pass through the barriers by tunneling. So a disordered quantum system should be an even better conductor than a disordered classical system. That's what everybody believed. And if you do a calculation of the conductivity, this is what you find. And you can check that all the corrections are negligible and so on and so forth. Wrong. Completely wrong. The guy who understood this is Phil Anderson. There is a remarkable paper in 1958, which is absence of diffusion in certain random lattices, which we now know as Anderson localization. What Anderson discovered is that in the same way than with a periodic system, you get these interferences, they also occur with the disordered system. And actually, if you take a 1D disordered systems, instead of having a metal, you get an insulator with exponential localization of the wave function. And this is something that has been incredibly interesting and incredibly interesting to understand mathematically. I won't summarize all the works that were done on this. I just want to mention one name because you see it every day on the patio near the blackboard. It's Elihu Abrahams, who was a main player in something called the Gang of Four, where they build a scaling theory of this phenomenon. And this is a remarkable phenomenon. I won't comment on this, just to say that, again, you can do a quantum simulation, and this was done with cold atomic gases, where in the group of Alain Aspect and Massimo Inguscio, and you can take a BC and free it in a random potential. And then what you will see is this exponential localization of the wave function. And this, you can do quantitative measurement on this. You can confirm on non-interacting particles, because of course, in the solids, the electrons interact. What are the properties of this disordered system? The main question is what happens when you have interaction. And again, I won't have time to really discuss this problem, but this is a very challenging problem, which is active at the moment. People are trying to understand what happens in a random potential if I try to study properties of systems, bosons, or fermions in presence of interactions. So here again, you can do experiments. Here is an experiment where people control the strength of the interaction and control the strength of the disorder. And this color code is the sort of width of the single particle correlator. So when it's blue, it's a superfluid. When it's red or yellow, let's say it's a localized object, which people call a Bose glass. And understanding the physical properties of this is something which at the moment is an extremely challenging question. So let me skip this, but that's good. I was on the right slide. So let me conclude. So yes, there is a difference between an electron and an autobus. It's not maybe what you would have expected. The reason is that one is a wave and the other is not. But the other reason is that the electrons obey the Pauli exclusion principle and not the autobus. Technically, let's say if the autobus were not repelling each other, you would have no problem understanding transport by autobus. We have more seriously in the community at the moment trying to study novel and non-trivial excitations. And of course, transport is a fantastic probe for understanding this. It's complemented by many other probes, but this is clearly one of the most interesting. And we have a novel situation, many effects. I didn't talk about the Hall effect, which was the image you saw together with the poster of the colloquium, but there are very interesting things to understand there. And there are many challenging, both theoretical, methodological, and experimental questions. So this is a fantastic world, and I think it's definitely worth exploring. And on that, I stop, and I thank you for your attention.
Questions, comments? Yeah. What do you transport? You mentioned charge.
Yeah. So of course, I had only 1 hour. I would need 1 or 2 weeks, but you can transport charge, you can transport spin, you can measure longitudinal transverse transport. If you put a magnetic field, you can also measure Hall effect, you can measure energy transport, you can put a gradient in temperature and measure the charge, the spin, or the Hall transport. So the possibilities are limitless for what you call transport. There are even other probes that you can construe as transport measurement. One of those is, for example, the neutron scattering. If you measure neutron scattering experiments, you will measure for example, the spin-spin correlation. And if you think about spins as representing bosonic excitation, it's like measuring a density correlation of the associated bosonic degrees of freedom. And if you measure density by continuity equation, you're also measuring current correlation. So there are a lot of experiments that fall in the category of transport.
Yeah. So let me just say, this is one of the best matter talks I've ever heard.
Thank you very much.
I followed it all the way through.
You can stop there. That's perfect. Oh, sorry.
I had a question. Is particular conductor insulator, which you might want to call like a semiconductor, but maybe need a different name. What are the practical applications?
These materials, I would say today, no practical applications. When people discovered them, they thought it would be the route to high temperature superconductivity. Because these were the first organic conductors, plastic, that were showing superconductivity. And actually, the temperature raised from 1 Kelvin to 10 Kelvin. Then the cuprates came with TC, which were 130 Kelvin, and this route was abandoned with this. But again, the applications is not the main point. This is showing very interesting phenomena, physical phenomena, and this is one category of materials in which you can study them. So if you want applications or if you want basic phenomena, let's say it's not the same game. For me, I'm a theorist, so I'm more interested in the basic phenomena. If you ask me, for example, what is the application of the fractional quantum Hall effect, I think the honest answer is zero. But it's a fantastic phenomenon.
Like
Semiconductors, a lot of interest. By the way, there are parent compounds, not these ones, but polymers which were developed by Alan Eager, who led to plastic electronics, and Alan Eager got the chemistry Nobel Prize for these discoveries. So not these ones, but in the global family, there were fantastic applications.
Well, give it biophysics.
Okay. Yes. There, I'm trying to remember what I learned more than 20 years ago in the class. So I remember the one-dimensional quantizing model come back to a 2D classical model. That was related to what you're talking about here?
So part of it is related. If you try to do, for example, the 1D equivalent with bosons, I don't think I have a slide, but if you try to take, for example, a 1D chain of bosons in a periodic potential, you try to put one boson per period of the potential. This is a quantum problem. This can be mapped. So this is 1D quantum. And this can be mapped onto a 2D SY model, which has a BKT, a Berezinski-Kostelis-Thouless transition. The Mott transition in this material is the BKT transition of the 2D classical XY model. There have been beautiful measurements on this system by someone named Hans-Christoph Nagel in Innsbruck. And I think these measurements are actually the best measurement of the BKT transition you can imagine. By using this mapping in an intelligent way, you can be freed by most of the problem that you have if you try to do the thing directly on the 2D system. Yes, you're absolutely right. People can exploit, both theoretically, but also even practically, this mapping between, let's say, D quantum and D plus Z. Z is usually 1 or 2. It's the so-called dynamical exponent. Depends on the relation between the momentum and the energy. Classical problem. Now, this is true for equilibrium phase diagram. When you start looking at transport or our out of equilibrium properties, the mapping kind of breaks down because the time here is not the time here. So when you look at equilibrium, the time is acting as Z additional dimension. If you start to be out of equilibrium, we don't know what to do. And that's one of the active questions to see if we could exploit something a little bit similar.
Would you comment on the attempts to compute transport using holographic, holography, using hydrodynamic principles? Instead of thinking about glorified quasi-particles, and that's how we say there are no quasi-particles, there's some permanent flow. What's your personal opinion? Is there future in this? Is it success?
Okay. Short answer is no. Don't want to comment. No. So more seriously, more seriously. So yes, there have been, so maybe it's a question a little bit for specialists. There have been recently a lot of attempts to build hydrodynamic theories. But, hydrodynamic theories are built with the ideas that the only thing which is conserved is the number of particles, essentially the energy, and more or less that's it. And therefore, you stop there and you build an equation where you get equations for these quantities. But, for example, especially in 1D, there are models which are integrable and which have an infinite number of conserved quantities. And if you don't take this into account, all your hydrodynamic descriptions will be wrong. So people have built description like this. It goes under the name of generalized hydrodynamics. I think it's a very good, a very fruitful line of attack. And but it's not the only way. You can also take other theories and use a renormalization group. And then you have to determine what is the leading irrelevant operator that not commute with the current you're trying to study, because it's the one that will cause the scattering and the decay of this current. So there is a very fruitful galaxy of attacks, I would say, building on this. We are trying to find methods that would work in not on a one-to-one basis, but which would work in a general way. For example, when do systems diffuse or do not diffuse? Whether the system stays a perfect conductor at finite temperature or not. And so far, only partial success.
So my old world, long time ago, but I was wondering if you could comment on with these cold atom simulators, you could measure many, especially the optical ones. It seems like you can measure stuff you could never dream about measuring even 15, 20 years ago. I was wondering how you think that's impacted the kind of theoretical calculations that are doing that you can do, or how the ability to probe these systems with so much more resolution experimentally has changed the way theorists or the way the community is thinking about this.
So this is a very, very good question. So first, I cannot measure anything, but he can. So let's be more serious. So you're absolutely correct. The cold atomic systems have provided a world which is complementary to condensed matter. It's complementary for two reasons. And I think the first reason is even more important than the second, is the degree of control that you have on the system. You can tune the interactions at will, you can tune the kinetic energy at will. Interactions are short range. You can also create long range interaction, but they are short range, which allows you to sort of, for theorists, fall on the model you know and love. Now, the second thing that they brought is, of course, new probes. For example, one thing which is fantastic is that if I have this system here, I can give you a snapshot of the density on every site without the averaging. Which means if I want to average not the density or maybe Ni and J or whatever, but if I want to average exponential of I log of hyperbolic sine of the density to the power, the density at another site, can do it. And that's fantastic because there are, string order parameters which have been invented in some system like spin-1 chains for which it's useful. So this has opened a whole new way in thinking in probing the system. Now, there are two faces in a coin, and you have also to realize that this system, they are not at that stage the ultimate solution of everything. First, you don't get 10 to the 23 particle, but only 1,000, 10,000, 100. Second, when it's fermions, the temperatures, typical temperatures today, are TF over 10, TF over 20, which means in condensed matter language, an experiment at 1,000 Kelvin, where you would melt not only the sample, the lab and the experimentalist. So one has to use two worlds in the place where they are strong, and one shouldn't oppose these two worlds, but on the contrary, make them interface, understand what is the questions that the other world is bringing. For example, one thing for which cold atoms were fantastic was to study out of equilibrium physics. And this is something that is coming to condensed matter, with pump probe experiments and so on and so forth. So I think it's a very exciting world to have these two experimental systems which are complementary and which have open whole world of new study, new way to think, which one can bring the condensed matter, and vice versa, bring some of the questions of the condensed matter to this world, and maybe also use some of the condensed matter systems as quantum simulators, both for condensed matter and cold atoms. For people doing quantum spin systems, can use quantum spins as quantum simulator for Bose-Einstein condensate. So this is something which we need to integrate, I would say, in the field. Sorry, but just to say, these are fantastic new systems that, of course, help a lot.
Let me remind you that everyone is invited to the wine and cheese outside, and let's thank Thierry one more time.